at our fourth type of reaction with double replacement reactions. So our goal for today is that we will be able to predict the product of a double replacement reaction. Okay, so you guys remember the way to recognize a double replacement reaction is we have two compounds as our reactant. Okay. So if we look at this example, we have a compound with Peach and Daisy and another compound, Mario and Luigi. So we have two separate compounds here. We'll call them compound AB and compound CD. When they undergo a double replacement reaction, our two cations or two elements in each of those compounds are going to switch. Okay, so here we can see Peach replaced Luigi to form a new compound, AC, or a compound with Peach and Mario. And then we can see in our second compound, Daisy replaced Mario to form another new compound, BD. So that's why it's a double replacement reaction. We have two things being replaced here. Okay. So when we go to predict our products, our two cations, which will often be our two metals, will switch with one another. So we'll start off with our two compounds as our reactants, and then our two cations, which will typically be our metals, switch with one another. Remember, a cation is going to have a positive charge. Cations are positive. Okay. So let's go ahead and look at some examples. Aluminum sulfide. So we're going to start these the same way we did all of our previous reactions. Our first step is to write our formulas of our reactions. Okay. And we know in order to write our formulas, we need to look at our charges. So if we look at calcium on the periodic table, calcium is going to have a +2 charge. Hydroxide, that's one of our polyatomic ions. So we would have to look at that polyatomic ion sheet and see that the formula for hydroxide is OH minus 1. We can't just assume the formula for calcium hydroxide will be CaOH because we need to balance those charges. So if calcium is +2, hydroxide is -1, we would need 2 of those hydroxides in order to balance out our charges. I'll leave those. Okay, so that calcium hydroxide is reacting with aluminum sulfide. So we need to add aluminum sulfide to this reaction. Aluminum, that's Al, and if we look at the periodic table, it has a charge of +3. Sulfide, that's just going to be sulfur. Notice we have the IDE ending, and that tells us it's just a normal element rather than a polyatomic ion. And sulfide is going to have a -2 charge. Okay? So if we need our charges to balance here and to get the formula for that compound, we're going to need 2 of those +3 aluminums and 3 of our -2 sulfurs. Okay, so that way those charges balance out. Okay, so looking at this, we know this is a double replacement reaction because we are starting out with 2 different compounds. And when we predict the products of this compound, our 2 positive ions, so we have to look at our charges, see who is positive, and we're going to see that was calcium and aluminum, are going to switch. Okay, so just like how Peach and Luigi switched spots, so are our 2 positive ions. Okay, so that means in our new compound, we're going to have a compound with aluminum and hydroxide and a compound with calcium and sulfur. Make sure that when you guys write the formulas for your products, you write the positive charge first. Okay, positivity always comes before negativity. Okay, positive ion comes first. Okay, so we can't just assume these formulas are AlOH and CaS. Just like before, again, we need to double check with those charges. So we said aluminum was +3. hydroxides minus 1. So if we need those charges to balance, we're going to need 3 of those minus 1 hydroxides for a form of AlOH3. And then calcium has a plus 2 charge, sulfur has a minus 2 charge. So that one's already balanced. That one's good to go. Okay. So our first step, write the formula of our reactants. Then we determined the type of reaction. We knew it was double replacement. And then last, we wrote the formulas of our product. Okay, and then before we move on from this problem, we have to make sure we balance. Always balance the number of atoms you have on either side of that reaction arrow. So if we look at this, if we look at our hydroxide, remember, if we see the same polyatomic ion on either side of that reaction, we can look at that as one group. We have 2 hydroxides on our reactant side and 3 on that product side. We can't end with more than we started with. So if we want to have the same number on either side, we have to think, what does 3 and 2 both go into? And we know they both go into 6. So in order to get to 6 hydroxides, I would need to use 3 of my CaOH2s to produce 2 AlOH3. Because if I have OH3 2 times, I'll end up with 6 hydroxides. Okay, so now my hydroxides are balanced. If I look at my calciums, on my reactant side, I have 3 calciums, now that I put that coefficient of 3 there. On my product side, right now I only have 1. I can't start with 3 and end with 1. So that means I would need to have made 3 calcium sulfide. Okay, so now I have 3 calciums on either side. Look at my aluminum, I have 2 on my reactant side, and I have 2 on my product side. So aluminum's good. And then last but not least, sulfur. I have 3 on my reactant side and 3 on my product side now that I've made 3 calcium sulfides. So that one is also balanced. So now that we have the same number on either side of our reaction, now we are done. More challenging. So here we have magnesium nitrate and water. Okay, so same for stuff as before, always write out our formulas. So magnesium is Mg. Look at the periodic table, it has a plus 2 charge. Nitrate is going to be NO3, it has a minus 1 charge. So just like before, if we have a plus 2 and a minus 1, in order to get those to balance, we are going to need 2 of those nitrates, 2 of those minus 1 charges. Okay, so this is going to react with water. We know water is H2O. But here, in these double and single replacement reactions, it might be easier to think of water as HOH. Because we still have our 2 hydrogens and 1 oxygen, but it's just kind of easier to see who is going to be our positive ion and who will be our negative ion. Because we know hydroxide has a minus 1 charge, which means hydrogen has to have a plus 1. Whenever we are working with hydrogen here by itself, we are always going to assume it has a plus 1 charge. So whenever you're just looking at hydrogen, it's going to have that plus 1 charge. Okay. So now we know this is double replacement because we have 2 compounds as our reactants. So we know our 2 positive ions, so our magnesium and our hydrogen, they are going to switch places. So this means our hydrogen is going to kick out that magnesium and form a compound between H and NO3. And likewise, we know our magnesium is going to kick out that hydrogen and form a compound between magnesium and hydroxide. Okay, so again, whenever we write the formulas of our compounds, we need to make sure our charges are balanced. So we know hydrogen is plus 1, nitrate's minus 1, so those are already balanced. Those are good to go. However, looking at our magnesium hydroxide, Mg has a plus 2 charge, and on our polyatomic ion sheet, it tells us hydroxide has a minus 1 charge. So if we want those charges to balance, we're going to need 2 of those hydroxides, for formula being MgOH2. So remember, whenever you're writing the formula of a compound, always be sure to look at those individual charges. Okay. So now that we have our products written, we can go ahead and balance. Looking at our nitrates, and again, we see NO3 on either side of our reaction, so we can treat it as one thing. We see that we have 2 nitrates on our reactant side and only 1 on our product side. So in order for those to balance out, I would have needed to make 2 HNO3s. Okay. When I do that, now I have 2 hydrogens on my product side, and I only have 1 on my reactant side. So if I'm going to make 2 HNO3s, I'm going to need to have started with 2 water. So that gives me 2 hydrogens on my reactant side as well. Okay. So now when I use 2 waters, I also have 2 OHs. So if I start off with 2 OHs, I need to end with 2 OHs, which I see that I have written here. And then I have 1 magnesium on either side, so I know that I'm done and good to go. We see that Roman numerals, so we know we have a transition metal. So we'll go over some of the transition metal naming rules. So if you are feeling confident, go ahead and pause the video and see if you can do this one by yourself, and then check in to see how you did. Okay. If you're not up to that point at this time, let's go ahead and walk through it together. Okay. So our first step is to always write the formula of those reactants. And I'm sure you guys are tired of hearing me say this, but whenever we write those formulas, we have to look at those charges. So sodium, when we look at the periodic table, has a charge of +1. Carbonate, we see that ATE ending, and that tells us we need to look at our polyatomic ion sheet. Okay? And when we do that, we're going to see that carbonate has a -2 charge. So if carbonate's -2, we're going to need 2 of our +1 sodiums in order for that to balance out. That is going to react with manganese 4 oxide. Manganese is Mn. And remember, for those transition metals, we can't look at the periodic table to determine those charge, and that's what that Roman numeral is for. That 4 after the manganese is telling us that Mn has a +4 charge. That's bonding with oxide, which is just going to be oxygen. Okay, which looking at the periodic table, we know has a -2 charge. So if manganese is +4, oxygen is -2. We'll need 2 of our -2 oxygens for those charges to balance out. Okay. So again, we know this is double replacement because we have 2 compounds as our reactants. Okay, so now that we know our type of reaction, we can go ahead and predict our product. We know our 2 positive ions are going to flip-flop with one another. So if we look at our first compound, our positive ion was sodium. Looking at our second compound, our positive ion was manganese. That means our sodium and our manganese are going to switch places. So now we have manganese bonded to our carbonate and sodium bonded to that oxygen. And again, since we're making compounds, we need to look at the charges in order to determine the formulas of each individual compound. So we said manganese is +4, carbonate's -2. So again, in order for these to balance, we'll need 2 of those -2 charges in order for that to balance. And then looking at our sodium oxides, sodium's +1, oxygen's -2. So we'll need 2 of those +1 sodiums in order to balance out our 1 -2 oxygen. Okay. So from here, once I have my products predicted, now we just need to go ahead and balance. I have 2 sodiums on either side of my reaction. So that's good to go. However, I have 1 carbonate as a reactant and 2 as a product, which means I would have had to use 2 sodium carbonates. Now I have 4 sodiums on that reactant side, which means I need to end with 4 sodiums as well. So I would have had to make 2 sodium oxides. And now I have 2 oxygens on my product side, 2 on my reactant side. So we know our oxygens are balanced. And then for manganese, we start with 1 and we end with 1. So that one is good to go as well. Okay. All right. I hope that helped. If you guys have any questions, please let me know. Have a great day.